First, what is a wave? A wave is just the motion of some sort of disturbance. So if there's a disturbance created, like if you hit your hand on a table, you can hear the sound. It's disturbing the particles in the air. There's a wave, a sound wave traveling to you. The medium is the material through which the disturbance travels. So for example, a sound wave, the medium is the actual air around you that's carrying it. Mechanical waves are waves that require a deformable medium to travel, and this example is sound, because again, the molecules in the air vibrate, so the medium is deformable. The air itself, its molecules are changing, they're vibrating, they're deforming to carry the sound to your eardrum. The fourth term is a pulse wave, and a pulse wave is just a single wave. It'd be like holding a rope in your hand and just flicking the rope once. Whereas a periodic wave is a wave whose source is some form of periodic motion. So the source, meaning your hand, it continues to generate pulses one after the other. So a single wave, like just flicking your arm once and seeing the rope jump, would be a pulse wave. But continuing to do that with your arm would be considered periodic because the source, your arm, is continuing to generate pulses over and over again in some form of periodic motion. Let's take a look at two types of waves. First, we'll look at transverse waves. In transverse waves, the vibrations of the particles of the wave move perpendicular to the wave motion. So for example, look at a vibrating blade. So imagine that this blade is plucked and it continues to vibrate up and down. Well, first the vibrating blade is at the top, and the blade's going to come down, then back up, and then down and up. That's what you're seeing here. So the blade moves down, then you're here. The blade moves further down, you're down to here. Then it moves back up, and you get back to here. So this blade is moving up and down. Well, what's happening is causing this rope to look like this at first, then it's like this. So you're seeing this point in space on the rope is going to continue to move up and down like that. That's the point then moving up here, then the point is moving back down, then the point is moving down further. So you're going to see this wave continue to change its shape, and this point on the wave is going to move up and down. Well, the wave's motion is this way. But the particle, this point on the wave, right here, or here, or here, or here, is only moving up and down. So the motion of the particle is up and down, the motion of the wave is left to right, and therefore they are perpendicular to one another. Now, when describing a wave, we want to look at several characteristics. First, you'll notice that this wave here looks very much like a sine wave. And we'll see that there are certain terms we're going to use. First, the top of the wave is called the max or the crest, and the bottom is called the trough or the minimum. The distance from this midline right here to the top, or the distance from the midline to the bottom, is called the amplitude of the wave, the height in essence. And finally, the distance from crest to crest, or trough to trough, or origin, or meaning like midline, through the midline and back, so to here, so from here to here, is called the wavelength, which is really similar to the period of the wave that we're looking at if this were a time scale here. The second type of wave is longitudinal, and with longitudinal waves, what we'll notice is that the vibrations of the particles of the wave move parallel to the wave motion. So imagine if you had a spring attached to a wall, and you were to pull on the spring and then let go, the spring would vibrate this way, left to right. So we're going to see that the vibration is going to be left to right, and the wave's motion is left to right. So therefore, this is moving parallel to the wave motion, and it is a longitudinal wave, a longitudinal wave. And what you'll notice here on this graph, what's graphed is really the density of the spring. So in the beginning, the spring is compressed here. This part of the spring is stretched, this part is compressed, this part is stretched. Well, here's the compressed part right here. Here's the stretched part down here. Compressed and then stretched. So this is a function of the density of the spring. So see how dense the spring is here? It's at a high value. See how not dense it is, how stretched out it is? It's at a very low value. And it's compressed, or it's dense, it's at a high value. It's stretched, so it's at a low value of its density. So this is just an example with a spring. But again, longitudinal means it moves parallel to the wave motion. The speed of a wave is represented by the formula to start with v equals x over t, where we know it means velocity equals displacement over time. But in this case, the displacement is just the wavelength, how far the wave travels. So we're going to call it this symbol here. If we go back and look at the graph, we would have seen this symbol before, but I didn't define it. Let's define it now. Okay, this is called lambda. And this symbol represents the wavelength that's measured in meters. This we've already defined in earlier lessons, and this is called tau. And this represents the period, and its units are in seconds. So we've got wavelength over period, so meters over seconds. So velocity is still measured in meters per second. Next, what we'll notice is that if you remember, the period of a wave is also defined as 1 over the frequency. So if we put 1 over the frequency here, we could take this definition and write it as follows. Velocity equals wavelength. Now we can, instead of dividing by 1 over omega, we can multiply by omega over 1, or multiply by the reciprocal of this denominator here. So this just becomes V equals lambda omega, or V equals omega lambda. So the velocity of a wave is equal to its frequency times its wavelength. Example 1 says the wavelength of the sound wave produced by a middle C on a trumpet is approximately 0.72 meters. If the speed of sound in air is 343 meters per second, find the frequency or the pitch of this note. So we start with our givens. We're told that the wavelength lambda is equal to 0.72 meters. The speed of sound in air is 343 meters per second. And we want to figure out what the pitch is of this note, or the frequency in hertz. So we could start by saying, all right, well, V equals omega lambda. We want to solve for omega, so V over lambda equals omega. We divided by this lambda on both sides. Now plugging in, 343 over 0.72 meters per second over meters equals omega. This is going to give me a value of 476. Now, and notice here that the meters cancel out. Well, that leaves behind 1 over seconds. 1 over seconds. Well, 1 over seconds, that's the definition of hertz. So the frequency is 476 hertz. Example 2 says, calculate the wavelength of an X-ray, an electromagnetic wave, if its frequency is 3 times 10 to the 12 megahertz, and the speed of all electromagnetic waves in empty space are 3 times 10 to the 8 meters per second. So we can start by listing our givens. Omega is 3 times 10 to the 12 megahertz. The space, or the velocity in space, is 3 times 10 to the 8 meters per second. What we want to notice right away is that we have megahertz here, so we should indeed convert that. Well, mega is times 10 to the 6. So this is really 3 times 10 to the 12 times 10 to the 6 hertz. That's what a mega is. So this is really times 10 to the 18. So we're going to solve for our value of lambda, the wavelength, right? Lambda is the question. So we start with V equals omega lambda, divide by omega on both sides. So the velocity, 3 times 10 to the 8, over the frequency, 3 times 10 to the 18, is equal to lambda. And that's going to give us a value of 1 times 10 to the negative 10 meters for lambda. And in this case, it's useful to list this in nanometers since it's a small value, while nano is times 10 to the negative 9. So if I convert it to nanometers, it would still be 1 times 10 to the negative 1 nanometers. But to list that a little simpler, just make it 0.1, right? 1 times 10 to the negative 1, or 0.1, or a tenth of a nanometer. Okay, the wavelength, again, the wavelength of an X-ray. And that's why X-rays can, in a sense, penetrate your body. They're such small wavelengths. So when you get X-rayed at the doctor's office, the length of those waves that's actually going into your bodies and examining you and looking at the different densities of your bones and different things in your body is 0.1 nanometers. Now, if we take a look at waves and energy, we can see that there's a clear relationship between them, and it's not obvious, but let's talk about it first. A wave really transfers energy. And the reason it does that, it transfers the motion of matter rather than the matter itself. It transfers its motion. So the rate at which a wave transfers this energy, it really depends on the amplitude of the wave, how much it can carry, the amplitude. The greater the amplitude, the more energy a wave can carry in a given time period. And for mechanical waves, the energy transferred is proportional, right? The energy transferred is proportional to the square of the amplitude. So this is really why the amplitude of a mass spring system, when friction is involved, is going to decrease over time, because energy is being dissipated in the form of friction, and thus the wavelength or the amplitude is getting smaller and smaller. So imagine that here's your mass, here's the wall, here's the spring. This mass is going to oscillate back and forth until it gets smaller and smaller and smaller, and it stops and it goes closer and closer until the wave stops, or the oscillations stop because of friction. Again, it's dissipating energy. So notice how big the amplitude was, right? This was the amplitude initially. Then the amplitude got a little bit smaller. Then the amplitude got even smaller until the amplitude was tiny in here. So the amplitude is getting smaller because the energy is going down. And it makes sense. If energy goes down, amplitude has to go down. They're directly they're proportional to the square right there. And this application is called damping. Okay? When a spring eventually slows down, or an object eventually comes to rest after vibrational motion, it's called damping. And that's due to friction.